Module 4 of Population Growth and the Logistic Curve. In this module, we will do two things. We're going to take some of the functions we've met already, such as the exponential function or the logistic function, and fit them to data. And what we'll do is actually look at how well these functions fit our data. The second thing we'll do is find out the parameters of our function. So in the logistic function, we had some unknowns like the carrying capacity and R and A. Through this process, we'll actually discover what the values are. So let's take a first example where we fit some data to an exponential curve. Suppose you have some data points here, equally spaced data points. Perhaps you're taking some measurements of something fortnightly and they appear to be growing exponentially. It'd be nice to be able to say what that exponential function is. And you could draw an exponential function and kind of make it go through the dots. This is a bit of a haphazard way of fitting a function to data. It's much easier to fit a straight line to data. So what we'll do is we'll use some of the differential properties of the exponential function. Recall that the exponential function f of x, defined as ae to the rt, satisfies this differential equation, which is a linear differential equation. So if I was to take this f over here, it would be a constant function, and constant functions are very easy to identify. So we take our data, we take df dt, which we approximate by just taking differences divided by our time interval, which is usually just some kind of constant. Plot df dt divided by the f value. What we end up with is a constant horizontal line. So if I take my y-axis as df dt divided by f, and I take my x-axis as the function values f, then what I end up with is my data points falling roughly along this horizontal line. How well the data points fit your horizontal line tells you how well your data fits an exponential curve. So we have some kind of visual assurance that our function is actually exponential. Furthermore, on top of this assurance, it tells us what the value of r should be, because df dt divided by f is r. So from this graph, we are able to obtain the value of r as well. Knowing r and knowing one other population value will allow you to determine what a should be. And so this analysis gives you two things. It gives you some kind of assurance that your data fits this curve, and along the way you pick up everything you need to know about the curve. In 2014, the spread of Ebola in West Africa appeared to grow exponentially. Let's have a look at some of that data, fit an exponential curve to it, and see how well our data fits this exponential curve. Here we have the number of reported cases of Ebola in West Africa from the 22nd of March through to the 19th of October 2014. What we're going to do is approximate this information using an exponential curve. Before we even attempt to approximate this with an exponential curve, let's see if the data looks like it's growing exponentially. So I'll click on date, and then I'll hold shift and I'll click down here and select the date column and the number of reported cases column, and I'll go to insert, scatter, and click scatter plot. I get the number of reported cases, and as we can see, it's growing quite quickly. This tells us we're at least in the right ballpark for an exponential approximation. Good. As we spoke about before, what we're really interested in here is dp dt divided by p. This is going to tell us the r value in our exponential approximation. So we're expecting this should be about constant, and that constant will tell us the r value. We're going to build this up incrementally. We'll take differences in time, so that will be number of days between samples, differences in the number of reported cases, so that will be the number of new cases in this period, and then we can construct this quantity, dp, divided by dt, divided again by the number of reported cases. And that's going to tell us what our r value should be. Right. So I'll click on this cell and I'm going to do some arithmetic, and I tell Excel I intend to do arithmetic by pressing equals. And then I can do a date, this one here, minus another date, and it tells me that there are 7 days in between these dates. That's nice. So I can copy this, and then I press Shift and hold down and highlight all these cells, and I press paste. And what that does is not copy the number 7, but copies the formatting. So Excel recognizes that this number here is just this one minus this one. So the next one would be this one minus this one, and so on. And of course, this one here is a bit silly because it's this date minus nothing. So let's get rid of that. Good. I can do the same thing with the DPs. I declare my intention to do arithmetic to Excel by pressing equals, and I say it's this minus this. And 963 new cases in that period. So I click, I hold Shift and I press down and I paste. And you can see that this number here is bigger than this number here, but the reporting period is halved. So this is still growing exponentially. I'm now in a position to construct dp dt divided by p. That's equal to this quantity divided by this quantity, close brackets, divided by this quantity. Alrighty, and I'll copy that and paste it all the way down here. And I can see a bunch of values. I might plot them just to see if I can eyeball what the constant approximation to this information would be. So I'll select this one first. I have to select my x-axis first when I plot things. So this one first, because I want my p's down the x-axis and my dp's, dt's down the y-axis. So I hit Control and hold that while I click. And now I can do a scatter plot. And here I have my data points. And I can eyeball those and say, maybe it's 0.021.
With the R value in hand, we can attempt to fit the exponential curve with that R value to our data. And we fit it by selecting the right value of this parameter A. In order to find A, we just need one point in time. So let's select the point in time 22nd of March 2014. And at that point in time, there are 130 reported cases of Ebola. So let's fit that to this equation. We have 130 is equal to A times e to the 0.0121 times S. S being the 22nd of March 2014. And then I can just unravel this equation, and I have A is equal to 130 times e to the negative 0.021 times S. So we have all the parameters for our model of Ebola. We have an R value of 0.021 and we have an A value of this. Let's summarize all of that as P of t is equal to 130 times e to the 0.021 t minus s. Good. Let's see how this matches our data.
With the values of R and A in hand, I can see how well my exponential approximation fits with the number of reported cases I have. So this is equal to 130 times exp of 0.021 times by this date here, maybe I'll do brackets, times by this date here, minus, now I want the date, which is the 31st of 03/2014. I have to put string limiters about this, or quotation marks about this, to tell Excel that this is a date. And it tells me there's 130 people. Good. Let's copy that and paste it all the way along here. So seems reasonable match. Let's see how well this fits. So if I have my date first and then these two, I can click insert, scatter plot. There we go. And the number of reported cases matches somewhat well with the exponential approximation to the number of cases. Righty. We can also use this to predict how many cases there'll be in, say, the future. So if this exponential trend was to continue, I could say that on the 1st of the 1st, 2016, then I'll copy this and I'll paste it here. There'll be a lot of cases of Ebola. So that's almost 1 billion people with Ebola. And if that trend was to continue even further into, say, halfway through 2016, 01, 07, 2016, and I'll paste here, copy first and paste here, and there's 41 billion people on Earth with Ebola. But it's telling you that everyone will have Ebola by that stage. So it's a good thing that something has happened between 2014 and 2016 to stop the spread of Ebola.
Now let's suppose we have some data that appears to be logistic. Let's try and fit a logistic curve to this data. Of course, if I have my data points like this, just a few little data points that start off quite small and tend to grow, but not exponentially, they grow off to, it seems, some kind of limit. I'd like to put a logistic curve there that could tell me all about this data in its future, but I don't want to have to guess the parameters. I'd like some kind of rigorous method that would tell me about these parameters of my logistic curve, K and A and R. What we're going to do, as in the previous case with the exponential function, is use the differential properties of the logistic curve to turn this into a straight line, which we can then estimate quite easily. So, recall that this is our differential equation for the logistic curve. It's not quite linear, but if I divide everything through by p, then I end up with this. Some quantity, which is rate of growth divided by population at the time, is equal to some other linear function in p. Fabulous. All I have to do is plot this, and I'm expecting to get a linear function. Suppose we do this. I plot my points, dp dt divided by p, with respect to p on the x-axis. So on my y-axis I have the dp dt divided by p values, and on my x-axis I have the p values. My data points tend to clump up a bit. And how well they fit a straight line tells me how logistic my data is. Good, so we have some kind of visual method to tell how well our data fits a logistic curve. It tells us something else though. Because this function dp dt divided by p is actually just some gradient times p plus some y-intercept, I can take my straight line approximation to this data and just read off what the values of r and k should be. Excellent. So we've got two things. We've got some assurance that this data actually grows logistically, and we've got the values of r and k. All I need to complete my logistic curve approximation is one additional value, which will tell me one additional value of population. So I take time to be something and I look at the population of that time, and that allows me to solve for A. In module 3, we looked at world population and we saw that there was a point of inflection about the year 1999, and we used that information to then predict future world populations. Let's return to the problem of population growth and now fit a logistic curve to some real data, and thereby get a more accurate idea about what future world population will be.
So now we're going to do some logistic approximation to world population. Here I have a selection of world population data taken from the United Nations. This is the world population in billions to 2 decimal places, as well as the year in which the world had this population. What we're going to do now is approximate the rate of growth of world population as dp dt. So it'll be difference in population divided by difference in time measured in years. So dt is always going to be 1 in this example. And then we're going to look at dp dt divided by p and try and fit a logistic curve to this. And then we'll see how well we do. So let's begin. My dt, I'll click here, and I want that to be the difference between 1 year and the next. So this can be, maybe I'll start from down here actually, because my years are going in the reverse order to the previous example. So I'll start from here and say that that's equal to this year minus the previous year, and that's equal to 1. And just as in the previous example, I will copy this, and then I'll hold Shift and press up to select everything in that row, and I'll paste it. So the difference between 1990 and dt is apparently 1990. I'll just get rid of that. We won't use that value. And now we'll go to the dps. So here I want the difference between population in 1 year minus the other year. So this measures the rate of growth of population. Once again, I'll do equals, and then population in that year minus population in the previous year, and I get something to 2 decimal places. So I'll copy that and I'll paste it here. Good. So seem to be increasing about the order of 80 million every year. Right, now what I really want to do is look at dp dt divided by p. So let's do that. I'll have my dp's, which is that, divided by my dt's, which is always 1, but I'll just include that for completeness sake, divided by p. And I get that. So I'm going to copy that number and paste it all along here. I want this to be as accurate as possible. So I won't format this to 2 decimal places. What I will now do is plot this with respect to this. So if this is p and this is dp dt divided by p, I'm expecting this to look like a straight line. So I'll select this one first, and then I'll hold Control and I'll select this one. So I've got my x and my y. X is the thing you select first, y is the thing you select second. I go to Insert, Scatter, plot like that. And I'll put that up there, and I'll make it a little bit bigger. Good. So I've got all these lovely dots forming in some kind of negative gradient straight line. I'd really like to be able to say what this line is, and fortunately there's a way you can do that with Excel. If you right click on one of the data points, you can add a trend line, and you can even get it to display the equation of the trend line, which is fantastic. It's exactly what we want. Close that. Here's a lovely equation of a trend line. This tells us what we need to know about the logistic equation.
Assuming population growth is logistic, then dp dt divided by p should be linear. And Excel has told us that a good linear approximation to this quantity is 0.0275 minus 0.0023p, which, according to the differential equation for the logistic curve, should be equal to r minus r on kp. That means we can use this to determine the parameters r and k. R we just read off as being this constant parameter here, and k, well, k is equal to, well, r, negative r on k is equal to this quantity, and we already know r, so we can determine that k is pretty close to 12. That tells us a lot. It tells us that the carrying capacity of the Earth is about 12 billion people, which reinforces what we estimated this should be in our previous module. These parameters r and k tell us a lot about the shape of the curve. All we need to do now is find a, and a will center it to a particular population. So to find a, we only need a date and a population at that date. And let's use the fact that there were 7 billion people in 2011. And we only use this because it's convenient to work with 7. Good. So if we fit this logistic curve to our population, then that's P of 2011 is equal to 12 on 1 plus a e to the, and I'll leave it as r because that's cumbersome to write, so that's negative r times 2011, negative 2011 r. And that's supposed to be equal to 7. Good, and I can rearrange this equation. I can take that up there, and I find that 12 is equal to 7 plus 7a e to the negative 2011r, and 5/7 times e to the 2011r is equal to a. Excellent. I have all the parameters of the logistic equation. That enables me to write the equation that approximates the world population in any year t. That is, P of t is equal to 12 on 1 plus 5/7 e to the negative 0.0275 t minus 2011. Behold, the population of the Earth in year t.
First of all, let's take our logistic approximation and see how well it compares with the data we have in front of us. So this is equal to 12 divided by 1 plus 5/7 times x of r, which is 0.0275 times by my 2011 minus whatever year I'm in. And match up all the brackets, and we get that, which is pretty close. And maybe I'll format this to 2 decimal places. 2 decimal places, please. Good. And I'll copy that and I'll paste it everywhere. And that's lovely. I'm matching up pretty well. Let's see how well it matches. If I take this information and I go to insert, scatter, like that, I get a pretty good approximation. So I'll put that down there, make it a little bit bigger. I can't even see the blue dots. That's a pretty good approximation. I'm happy with that. Let's take this approximation into the future. Let's say what happens in the year 2020. Well, I have 7.7 billion people. What about in the year 2200? Then 11 billion people, or almost 12 in fact. And if I go to the year 3000, then I've got my 3 billion people. That's exactly what I was expecting. So we can see the power of the logistic equation. Just for kicks, why don't we see what happened in the year 1000? Then I've got 0 billion people. That's a shame. What about the year 1500? Still 0 billion people. Strange. I thought there were more people than that. 1800. Oh, there we go. We've got a few people there. 1750. Good. There we are. That's nice. 10 million people in the year 1750. So we can see our model going forwards and in reverse. Of course, there are some limitations with this model. We've assumed that the carrying capacity is constant, which of course is not true. But this model gives us some information about what future and past world populations would look like. So this concludes the course Population Growth and the Logistic Curve. I hope you enjoy using this curve to describe the populations of lots of interesting things.